Okay, so I will talk about this new loop expansion that we developed, okay, around the Bethe approximation. So usually the usual expansion is around the mean field fully connected model, and expanding around this model in some way we should obtain some prediction on finite dimensional systems. So just a few words about the Ginzburg-Landau construction of the Lagrangian. So take your favorite model. My favorite model is not SK, it's Ising model. And then identify the order parameter. So in this case, in the Ising model, it's the magnetization, so it's a scalar field. And then identify the symmetries of this model. So in this case, the spin flip symmetry. And then construct a Lagrangian that is the most general one with all the possible invariants of the symmetry that you identified, constructed with the field and its derivatives. And the coefficients are arbitrary, okay? I know you can, but I don't want, it's really, okay, so for the Ising model, the Ginzburg-Landau Lagrangian is this one. So you have a bare Lagrangian, these two terms, and then you have a quartic term with a coefficient that is g. So you can study what the bare Lagrangian gives you, so putting g equal to 0, and what does it gives you? It gives you, for the two-point correlation function in the momentum space, something that is usually indicated with the bare propagator, that is 1 over k square plus mu. And this mu is diverging at the critical point. So it's diverging at the critical temperature, for example, for the Ising model. And then you can introduce this g, and you can do a small g, not loop, a small g expansion around this L0. And then you have some rules to construct your Feynman diagram. So what is the next order? This is the order g of the expansion, because you just have a quartic vertex, so each vertex leads a factor g, and then you have, for example, the second order. Here you have two vertices, so this is of order g squared, and so on and so forth. So in the Ginzburg-Landau approach, that is around the mean field fully connected model, you have the vertices that are fixed. In this example, they are quartic vertices, and the expansion is in power of g. Okay, we will introduce a new expansion around the Bethe lattice, and we will see that this expansion will be in loop, in spatial loops. Okay, so how to construct this expansion? We need a small parameter to interpolate between the Bethe lattice and the finite dimensional lattice. So, which is this small parameter? Okay, take your favorite model on your favorite finite dimensional lattice. So my favorite model is the Ising model, and my favorite d-dimensional lattice is the two-dimensional lattice. Okay, then replicate your lattice m times. So I replicate it m times. So in this case, m is equal to 3, okay? And then, if a link ik was present in the original model, randomly permutate the link between the m layers. So here I have my ik on the original model, and then I permutate the links. So I take, for example, this one, and then this one, and then this one, okay? This is the random permutation of the link between I and k. And you should do this thing for all the links in your original model, in your original lattice. So for example, you have the Ising Hamiltonian. You can write the Hamiltonian for this replicated system, and then you can write the usual partition function, and you can realize that in the m equal infinity, you will have an m in front of everything, so you can take the saddle point if m is large, and this saddle point will give you exactly the Bethe solution of the model, so exactly the free energy of the Bethe lattice solution of the Ising model. So in the m equal infinity lattice, there are no loops. For this reason, we recovered the Bethe lattice free energy, because we don't have loops as happens in the Bethe lattice. And then we can study the 1 over m correction to this saddle point. So you can do in this way, but we prefer to do with the cavity method, because it's easier. Okay, and then at the end you can put m equal 1, and m equal 1 is your original model. So in my original model, so in my two-dimensional model, for example, I have spatial loops of all orders, so and of all length, while in the m equal infinity limit, I don't have loops. So the 1 over m expansion around this Bethe lattice will be an expansion in loop. So these loops are really spatial loops, not loops in the momentum. I mean, they will become loops in the momentum, but they are really spatial loops, so loops, topological loops. Okay, so let's look at which are really the terms in this expansion. So choose an observable, so for example, the two-point correlation function connected, so exactly this one, okay? And then for m equal infinity, we have said that we have a Bethe lattice, so if m is equal to infinity, this correlation function is exactly 0, because if I pick at random 2 points on a Bethe lattice, this will be at distance, an extensive distance, so the correlation will decay to 0. Then, which is the order 1 over m correction? So, with 1 over m, 1 over m is really the probability to have a linear path between the spin I and the spin j on the original model. So, this is the spin I, this is the spin k, this is the spin j. So, from I can go wherever I want in k. And then with probability 1 over m, I will pick exactly this layer, okay? I can go in m layers. I can pick the j that is in one of these m layers, but with probability 1 over m, I will pick exactly the j in this layer. So with probability 1 over m, I have a linear path on my original model. Okay, so what is the 1 over m correction to my two-point correlation function? Is the sum over all the paths of length L with this factor ZL. ZL is the number of such non-backtracking paths of the observable computed as if I am on a Bethe lattice, on a line on a Bethe lattice of length L. Okay, so what we are saying that the correlation between this point and this point at order 1 over m can be approximated with the correlation of all the paths, the linear path, considered as independent between these 2 points. Okay, so let's look to the 1 over m square correction. So at this point, the 1 over m square correction is the probability to have a single loop, because we have said that this path happens with probability 1 over m, and then I can go the other way. So I can go, for example, here, and then from here, the probability to pick again j on this layer is again 1 over m. So with 1 over m, I have this path. With 1 over m, I have this path. So the probability to have a loop, that is this one on my original model, is exactly 1 over m squared. So 1 over m squared is the probability to have a single loop. Okay, so on my original model. So a loop, in a loop we can identify 4 lengths. So L1, L2, L3, and L4. They are the lengths of the single branches of the loop. And so the correlation length at order 1 over m squared will be a factor, and the sum over all this length of the number of such loops multiplied by this thing. Okay, let's look to what these numbers are. So S is the usual symmetry factor of Feynman diagrams. It takes into account the symmetry, the exchange of the lines that you can, and the vertices that you can do. So it's known. I mean, open a book of field theory and you will find this factor S. And then we have this number of loops, and also this one is known. You can pick up from our paper. And it's just the product is proportional to the product of the number of single lines of length of this length. And these numbers ZL have nice properties. So you can construct the usual generating function as the sum over L of ZL lambda to the L. This is the usual definition for a generating function. And then the generating function in the Fourier space behaves in this way. So you can recognize this here, a propagator, no? We will see it later. So, and here we have this lambda C that is 2D minus 1. Okay, this is a property of the space, okay? And then, so you should multiply S, Z, and then this line-connected observable. So what is this line-connected observable? You should compute it for each model. So I choose the Ising model, and so I can compute this one. But if you choose your favorite model, you should compute this line-connected observable on your model. So how to compute it? This is the difficult part, because the other two are already done by us. So, yeah, okay. So how to compute this line-connected observable? So you compute your observable, the two-point correlation function, on this associated fat diagram. This is the fat diagram associated to this loop. So what is a fat diagram? Is a Bethe lattice in which we manually injected the loop that was on my original model. So here, these little branches here are the beginning of a Bethe lattice, but then there is this loop with exactly the length L1, L2, L3, L4. So you should be able to compute the observable on a Bethe lattice with this loop. And then you, to compute the line-connected observable, you should subtract the observable computed on the two branches of the loop considered as independent. So why you should compute this? You should subtract these two parts, because this one were the ones computed at the order 1 over m. So at the order 1 over m, you just consider all the linear paths as independent, but then you realize, no, these are not independent because they form a loop, so you should subtract the terms that you put in the order 1 over m. Okay? Is it clear? Okay, so this is the order 1 over m square of our expansion. So just two remarks. We have seen that the 1 over m expansion is an expansion in the number of topological loops. So, and we could have vertices of any types. So it's really different from the Landau-Ginzburg theory, because here the vertices were fixed by the theory. So here, for example, for the Ising model, we just have quartic vertices, and then the expansion is in the number of vertices. Here, it's in the number of loops, and the vertices can be whatever. So, for example, for the order 1 over m square, we just need one loop. So, this diagram can contribute to the two-point correlation function, and also this one. So, this one has two vertices, cubic vertices, and this one has one quartic vertex. Okay, so, okay, but for example, for the Ising model, we know that in the usual expansion around the fully connected model, this diagram is not present. So, what happens to this expansion, to this expansion around the Bethe lattice? Is this term present or not? And if it is present, for example, the question we can ask the same question for the random field Ising model, because also the random field Ising model is a quartic theory. So what happens to this term? is different from 0, and if it's different from 0, is larger or not with respect to the usual term in the usual Ginzburg-Landau theory. Okay, so let's see really how to compute these observables in the Ising case. Okay, so the 1 over m term, we should compute this A, L, B, Bethe, and we have said that this term is the observable computed on a line of length L on a Bethe lattice. So how to compute it? We know it, because we just have the transfer matrix method. So we know that the joint probability of two spins is a matrix. In the Ising case, it's a 2 by 2 matrix, and I can decompose it on their eigenvalues. Okay, and which are the eigenvalues of this transfer matrix? There is one that is 1, exactly 1, that is the largest one, and it corresponds to the eigenfunction that is exactly the Bethe distribution. So this Bethe distribution is the one that you can compute with the BP algorithm, for example. No? It's stable under update. And then you have another eigenvalue that is lambda max that goes to 2d minus 1 to the minus 1 at the Bethe critical point. So where there is the standard ferromagnetic transition in the Bethe lattice. So if you have hard spins, these are the only two eigenvalues, and then if you have, for example, soft spins, you have others. So you should sum over all the eigenvalues. Okay, but then I say that I want a connected correlation function, so I can just compute the connected joint probability distribution just removing this term, the Bethe-Bethe term. That's because the Bethe-Bethe term is just considering the spins as independent, so if I remove this term, I have the connected joint probability distribution for two spins. Okay, so let's put this form into the order 1 over m correction to the connected correlation function. I should sum over L, I should sum over lambda, and then I should sum over sigma x and sigma epsilon, sigma y, and then, okay, here you can recognize the sum over L, Z, L, lambda to the L. This is exactly the generating function for the number of non-backtracking paths that we indicated with lambda, Z lambda. And then you remember that Z lambda goes in this way with lambda C 2d minus 1. And then you recognize that lambda max exactly goes to lambda C at the Bethe critical point. So what happens is that it happens that this factor diverges at the Bethe critical point. So here I have a sum over all the eigenvalues, but then at the end I can consider just the largest one because it gives me a divergent contribution. So what we found is that the 1 over m correction to the two-point correlation function takes the usual form of a usual propagator, so exactly this one, the same of the Ginzburg-Landau theory, and with the mass that goes to 0 at the Bethe critical point. Okay, so the order 1 over m is exactly the same as the Ginzburg-Landau usual expansion. Let's look at the next term. Okay, I won't show you, but it's very easy to show that this diagram will give exactly the usual contribution of the Ginzburg-Landau theory. So let's look to the other one, so the strange one, the cubic one. So this is the formula for the second correction, so the 1 over m squared correction. We have this factor S, and then we have the number of loops, and then we have this line connected observable. How to compute the line connected observable? Well, it's easy enough, because for each line we should put the joint probability distribution that we found in the slide before, and then we should sum over these two internal spins, sigma 1 and sigma 2. Okay, so when we put everything inside here, you should see that you can group these terms depending on sigma 1 in a vertex function. This vertex function is just the product of the three eigenvectors with 3 eigenvectors, yes, associated to the 3 eigenvalues here. And okay, so as we did before, we would like to put here for the eigenvalues lambda max, because we have seen that the critical one that gives us the divergent behavior. But there is a but, because the eigenvector associated to lambda max is odd. So the vertex is, when we put all the 3 eigenvalues equal to lambda max, is an odd function of sigma, and then we sum over sigma, so we obtain 0. Okay, so we cannot put lambda max. I mean, we can put it, but we obtain a 0 correction. So this diagram for the Ising case is exactly 0. So what we obtain, we just recover the Landau-Ginzburg usual expansion for the Ising model. Okay, we are happy. Why we are happy? Because the Bethe transition, ferromagnetic transition, is exactly the same as the fully connected ferromagnetic transition. So expanding around the 2 model gives us the same expansion, with just the critical temperature that is different, as obvious. Okay, so we're happy. But it was really a simple model, so we could look to more complicated model, and here we are with the SK model, with field at t different from 0, and we computed the loop correction around the Bethe lattice in the limit of the connectivity that goes to infinity. I don't want to be to bore you with very tedious computations, but I just want to sketch the results. So, okay, this is the usual formula for the first correction around the Bethe lattice. Which observable we want to take? In the spin glass case, we have many 2-point correlation functions, the connected, disconnected, total, okay. But we can take this observable, that is a 4 replica indices matrix n squared by n squared, defined in this way. And with this observable, taking the correct sum of replica indices, we can recover all the possible correlation that we can define on the spin glass. Okay, so we should compute this observable on a line on a Bethe lattice of length L. So we can expand the partition function because we are in the limit of the connectivity that goes to infinity. So the coupling is small, we can expand it, and then we can introduce another n squared by n squared matrix. Okay, and then we can realize that the correlation function is just the product of this matrix to the power L, exactly as before. Before, we had the decorrelation function was the power some matrix that was the transfer matrix to the power L. Here we have exactly the same thing, with the exception that we have some replica indices. Okay, so as before we find the eigenvalues of this matrix. We have one critical eigenvalues that, as usual, is called the replicon that goes to 1 at the Bethe critical point. And then we have 2 degenerate eigenvalues, that is the longitudinal and the anomalous. They are degenerate and they are smaller than the critical one. Okay? So inserting this definition inside the definition of the order 1 over m correction, we can obtain the 1 over m correction to all the possible spin glass correlations. And you can see that, as before, we just have one eigenvalue to the power L. Okay, exactly as before. The only difference is that here you can have also a term that is L multiplied by eigenvalue to the power L. So there is this factor L in front of this eigenvalue. This is not a problem. I mean, at the end, with the spin glass, we obtain exactly the same things as before, because this lambda L is not critical, so we can neglect it. But it will be important, for example, in the random field Ising model. So just remember it. And okay, why there is this L here? Because of the degeneracy of the eigenvalues. Remember it for the future. Okay, so when you insert this expression inside the usual expression for the correction of 1 over m, we obtain exactly the same thing as before. So exactly the Baire propagator, okay, diverging at the Bethe critical point. So what about this term? Okay, we can compute this term. We have some vertex that is now a 6 replica indices matrix, but okay, we can do it. We have some just few replica indices to sum over, but okay. We obtain some results for the one loop correction. For example, for the connected correlation function. And what's nice is that here you have all these ugly coefficients, but you realize that they are exactly the same coefficients as the Breyer-Roberts expansion. So in the Breyer-Roberts expansion, they are computing the first order in the Ginzburg-Landau model, in the Ginzburg-Landau-Hamiltonian, but the Ginzburg-Landau-Hamiltonian for the spin glass has cubic vertices, so the first correction is, at the end, is this one. And so you can recover it. You can recover exactly the same coefficients. So even in this case, we just recovered the usual results. Okay, so why to introduce a new expansion to recover old results? Because it's not always like this. So third example, the random field Ising model at t equals 0. So the usual Ginzburg-Landau expansion is a Ginzburg-Landau expansion in which you have quartic vertices, but then you have two types of correlation functions. So you have a single pole, so the usual Baire propagator that is associated to connected correlation functions, and then you have a double pole here associated disconnected correlation function. And then you have some Feynman rules to construct Feynman diagrams of all order. You have some rules to construct the most divergent diagrams, and you can realize that looking only at the most divergent diagrams of the usual Ginzburg-Landau expansion, you obtain the dimensional reduction. I won't explain what dimensional reduction is because Victor did it this morning. Okay, so you know everything about it. So what about our expansion? So dimensional reduction is wrong. What about our expansion? Is our expansion consistent with the Ginzburg-Landau expansion or not? Okay. So first of all, we analyze things at t equals 0 because, as Victor said, the critical point is at t equals 0. Okay, so as you, I put again this formula, how to compute this AL on a Bethe lattice. We just realized that if you want to compute an observable on a line on a Bethe lattice, and then you have this sigma 0 and this sigma L, you can write this as just an Hamiltonian made of one single coupling, J, and two effective fields, U0 and UL, on the two spins. And this, and then what we found is an ansatz for this coupling and these effective fields at length L. So you have an ansatz, okay? Just few words on how this ansatz is. Okay. Okay, so you have an ansatz, you can compute your Baire propagators, and you obtain exactly, for the connected correlation function, the Baire propagator of the usual Ginzburg-Landau expansion, and for the disconnected correlation, the double pole. Okay, so far so good. What about this loop? Well, what we found is that this loop gives zero contribution to the connected correlation function, but it gives a non-zero contribution to the disconnected correlation function. So this loop should be inserted in an expansion around the Bethe lattice. So we are happy, but this term is subdominant with respect to the usual one. Oh, okay, so this means that dimensional reduction should be valid at order d minus 6 minus epsilon at least. But then the next terms could be relevant. So at a certain point, these cubic vertices could become important. But then on the avalanches, so if we insert cubic vertices on, in the computation of the avalanches, we can see that they are really important. So in the computation of the this new expansion can give us predictions on the avalanches. And this is really new because avalanches are really a finite connectivity phenomenon. And in fact, you cannot really obtain any prediction on avalanches just based on the usual Ginzburg-Landau expansion. So we obtain the usual scaling for avalanches, and we are really happy. And okay, these are the conclusions. We introduced this new model to expand around the Bethe solution. It's not useful in cases in which the critical points are the same for the Bethe lattice and the fully connected models, but it can be really useful in models in which the Bethe lattice transition is different from the mean field fully connected transition, as in the case of the random field Ising model, and also in the case of the spin glass in a field at t equals 0. But okay, this is some preliminary results.
Questions? We're a little bit behind time, so I think we'll hold questions for
Not
later.
for my fault, huh? It was Luca.
Did I miss a question? Nope.
Okay.
Thank you again.